Dream to become the next Sir Isaac Newton or Albert Einstein? Learn from the master. Refath Bari. Watch his videos to achieve your dream.
Matrices, and of course we're looking at a very particular type of orthogonal matrix today, which is of course the rotational matrix. Okay, now first and foremost, our do now is to go ahead and write down the rotational matrix. You should recall it, or you can derive it, because we actually derived it from the past few lectures. So go ahead, try to derive the rotational matrix, and I'll give you a few seconds. Let me just adjust my camera while I'm at it, and I think we'll be good to go. So let's just tip this camera up, and boom.
For the people who haven't catched up recently, can you explain what an orthonormal matrix is?
Yes, an orthonormal matrix, good question. An orthonormal matrix is a matrix that has components that are orthogonal and normal matrices, okay? So I'll explain what all of that means very soon, so don't worry. But first and foremost, as I said, for our do now, we're going to go ahead and write down the rotational matrix, which is as follows, okay? Now, of course, if you don't actually remember the rotational matrix, that's fine. I'll introduce some handy-dandy tricks that you can use to recall the rotational matrix, just in case you don't want to do the full derivation. But here it is to the folks out there. Just ignore the noise, but we have cosine theta, sine theta, right? Just simple x and y components right there. But then for my next x and y components, I'm going to have negative sine theta, cosine theta. Okay, now what's one way to take a look at this? Well, first and foremost, you might notice that I have cosine and sine just as regular on top and bottom. So for example, any given point on a unit circle will have coordinates cosine theta comma sine theta, assuming that that angle makes an angle of theta to the horizontal, right? But what about negative sine theta cosine theta? Well, in which case will we get negative sine theta cosine theta? Is it a reflection by 90 degrees, a rotation by 180? In what case? Well, let me show you. In what case do we switch the coordinates and negate the x coordinate? Well, let's take a look. Let's say we have something like this. Here I am in my full two-dimensional coordinate plane. Hopefully everyone sees that. Let me just check whether the live viewers see that. Yes, they do. Okay. So, what will I have? Let's say I have a random point up here. I don't know, that's 1, 10. Let me just ask my student right here, my live audience, whether he's taking his notes and he's actually doing as promised. Now, let's go ahead and continue our discussion, right? So if we have this point 1, 10, what is its rotation 90 degrees going to result? Well, let's just draw the segment from the origin connecting to this point, and let's rotate this by 90 degrees. That's going to land us somewhere right over here. And what is that point? What is that resulting 90 degrees rotational point? Well, first and foremost, you can see that my coordinates will be switched, right? Instead, I'm going to have negative 10, 1 here. And you can see what I just did, right? All I did was a rotation of 90 degrees around the origin of what? Whoops. You also have to write around what point you're rotating, which in this case is the origin. And the point I rotated was 1, 10. Rotating it by 90 degrees, is it clockwise or counterclockwise? I just did it counterclockwise, so let me go ahead and highlight that. I rotated this point 90 degrees counterclockwise, as you can see right there. So the resulting point happened to be negative 10, 1, but that's not the main lesson. What that tells us is when I rotate any point by 90 degrees counterclockwise, what am I going to get? I'm going to get the coordinates of the points flipped, right? So instead of 1, 10, I'll have 10, 1, and the x coordinate negated, right? And that's exactly what I have right here. I have cosine theta and sine theta flipped, so sine theta, cosine theta, and I have the x component negated, so I have negative sine of theta. Okay, so hopefully that gives you a brief overview of the rotational matrix. Now what we're going to do is go ahead and take a look at a very interesting property of the rotational matrix.
I believe a man is doing a lecture right now.
Yes, yes. So let's go ahead and in our lesson we're going to actually take a look at the inverse. The inverse of what? Of the rotational two-dimensional matrix. So let's erase all of this. Now let's take a look at our lesson. Okay? So here we go with the inverse of our rotational two-dimensional matrix. First and foremost, what is our rotational matrix? Well, as I just discussed during my do now, I have cosine theta, sine theta as normal for my first vector, and then I flipped the components and negated the first one. So negative sine theta, cosine theta. So you can almost imagine it as taking whatever this vector is and rotating it by 90 degrees to get this second vector. Okay, hopefully you're seeing what I'm doing out there. Okay, now my goal is to find, number one, I'm going to find two things. During the lesson, I'm going to find the inverse of this matrix, okay? Now, how do you find the inverse of any two-dimensional matrix? Well, because it's a square matrix of order 2, I simply know that I can use the formula 1 over what? 1 over the determinant of this, which is going to be given by AD minus BC, right? That's going to be my determinant. And I'm going to take that scalar, because the determinant is, of course, going to give me some scalar quantity. I'm going to take that scalar and multiply it by what? Just multiply it with the vector itself, right? But no, we're going to switch the main diagonal. So cosine theta, you switch them, you'll still end up with cosine theta. And then what do? Well, if you forget, you can always hark back to the original formula, right? So if you have any matrix A, B, C, D, of course it has to be a square 2 by 2 matrix. Its inverse is going to be given by 1 over AD minus BC, 1 over the determinant, times what? Well, we're going to flip the main diagonal, so instead of AD we'll have BA, and then we're going to negate the second to main diagonal, so we'll have negative B, negative C. Same exact thing here, so instead of negative sine theta and sine theta, I'll have sine theta and negative sine theta. So it's just a little bit of sign changing and not much else. Sine theta, negative sine theta. Okay, but we're not done. All we have to do now is plug in for A, B, C, and D, so that we can actually get the value of the reciprocal of the determinant. So what are we going to get? Well, let's take a look closely here. So 1 over what? Well, AD, I'll have cosine squared theta, right? Hopefully this line can be drawn straight. So I'll have 1 over cosine squared theta minus BC. What's BC? BC is going to be negative sine theta, sine theta. So it's going to give me negative sine squared theta, and then I'm subtracting it, so I'm going to have a plus sign. So plus sine squared theta. And of course all of this is going to be multiplied by the original two-dimensional rotational matrix. Okay, so now I'm just going to end up with a scalar value for the determinant here, because of course, as you should know by the trigonometric identity, sine squared theta plus cosine squared theta is none other than, let's check if our viewers are actually watching. Yes, they are. This is just going to simplify to 1, right? And so the inverse of my rotational matrix is just going to end up being cosine theta, sine theta, across the horizontal, across the row, and across the second row I'll have negative sine theta, cosine theta. Okay, good. So that right there is the inverse of my rotational matrix. Now, many of you may be questioning, what's the big deal here, Refath? Right? What's the big deal in doing that kind of a thing? Now, why don't we?
Where's the other computer?
That's right. So why don't we just go ahead to the exit slip now? Now that we found the inverse of the rotational matrix, we're ready to go on to the exit slip. In the exit slip, we're not going to find the inverse, we're going to find the transpose of this rotational matrix. So let's go ahead to the exit slip. Now I'm going to give you a few seconds to go ahead and do the exit slip. So go ahead, find the transpose of, you know what, instead of writing -1, I should actually write T as in transpose. Okay, so go ahead, find the transpose of this rotational matrix, and I'll give you a few seconds. Good luck. Okay, hopefully that was enough time to find the transpose, right? It should be fairly basic. All you have to do is flip along the main diagonal, and if I do flip along the main diagonal, what will I get? What will I get? I'll get simply cosine. Let's write the transpose in a different color. Maybe we'll write it in dark green, right? Just to switch up the monotony. Okay, so we're gonna have cosine theta, and then what? And then sine theta across the first row, right? Why? Because I'm just switching along this diagonal, the second to main diagonal, right? And then what am I gonna have for my second row? Well, my second row is simply gonna be negative sine theta, so negative sine theta, and the final entry will be cosine theta. Now you should be noticing something, and what is that something? As you can see, the inverse which I've written in blue and the transpose which I've written in green are equal. Okay, the inverse of the rotational matrix is equal to the transpose of the rotational matrix. That is extremely important, right? Because that tells us that when we reverse this rotational transformation, it's gonna give us essentially the same thing as the transpose. So how can we mathematically write that down? We can actually just go ahead and write down the inverse of the rotational matrix, which I can write using r to the power of -1. Remember, it's not an actual exponent, this is just for notational brevity. So I'll have r to the -1, so the inverse of my rotational matrix is equal to its transpose. And as a matter of fact, as you may conjecture from this is not the only case where the inverse of a matrix is equal to its transpose. As a matter of fact, you can conjecture for that most orthonormal matrices will have their inverses equal to their transposes, okay? So this is one of the most crucial properties that make orthonormal matrices special. Their inverse is equal to their transpose. Okay folks, thank you for watching.
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.